Okay, let's get started. So welcome everyone to our first hands-on training on scientific machine learning. And we are, today is not just myself. Actually, Levi will be the main instructor for this one. So I'll be taking about 25 minutes to introduce the scientific machine learning, the basic methodology. And then Levi will be leading everyone through the TensorDiffEq, TDQ. And then there will be a 1-hour hands-on session after that. So let me first introduce myself. My name is Jian. I'm a research scientist at the TAMIDS, Texas A&M Engineering Experiment Station. And I'm also affiliated with Institute of Data Science and High Performance Research Computing. So I'm co-leading this scientific machine learning laboratory with Ulysses, Dr. Ulysses, and we are, trying to promote. We have been working pretty hard to promote scientific machine learning here on campus, and we want to get more researchers here and engaged in scientific machine learning research, and we are interested in your involvement in future development of proposals and also the research projects. And so today we'll let's get started then. So this is a new laboratory started at TAMIDS about I'm not sure, it's probably end of last year and early this year. It's around that period of time. We have 3 pilot projects in the lab, and we have researchers from engineering, college engineering, college science, and we are trying to, starting small, but we are going to expand, in the coming years. So one of the main software development along this line is a TensorDiffEq. That's a Python package built on top of TensorFlow 2.x. Levi and also Ulysses, they are leading developer for this software package, and it's a really, really powerful tool, as you'll see today. And we are very interested in promoting it among our local community, and also we want to get everyone involved in the future development, and hopefully we can really establish some national brand with this piece of software. And it's really a great piece of software, and I really like it myself. And Levi is doing a very good job getting the documentation and all the all the modules well organized. So I'll first introduce a bit more about scientific machine learning at a very high level, and I gave almost identical presentation at HPLC short course, as one of HPLC short courses. That's probably last month or not so long ago. This one is more or less similar to that one, but the hands-on session will be mostly focused on TDQ. The previous one I hosted at HPLC was focusing on the Julia package, which is doing something kind of similar to TDQ, but it's a completely different framework. But I think this one will be more interesting, as firstly, it's a local development. Secondly, it's a very, very, very powerful, based on TensorFlow 2.x, and gives you more freedom to play with the software, etc. So the materials I used for these slides are based on a workshop report from from a DOD and a DOE, and they are preparing, they are preparing a lot of materials based on the latest development in the field. And also there is a very popular paper in the field, it's a physics-informed neural networks. And that one probably is laying the foundation for a lot of work that TensorDiffEq and many other similar works are based on. So if you're interested, probably you want to go to take a look at the paper, and there are some other following papers, doing something similar. So talking about scientific machine learning, we needed to go back to think about what the main motivation behind it. For traditional scientific computing, like many of us who are involved in modeling using the mathematical formulas, and then come up with algebraic equations based on your mathematical models, and then you start writing your code. And after your code is ready, you get some new input and make predictions. That's the traditional scientific computing methodology. And so what we call it's the theory-driven modeling, either numerical simulation or numerical modeling, whichever you call it. But we do have a governing equation there. So for almost all the papers in scientific computing, you start with the governing equations, and then you talk about your methodology, how you discretize your equations, what's the numerical algorithm you are developing, etc. So that's a traditional way of doing scientific computing. But with the rapid development of deep neural network technologies and also all the AI-driven methodologies in the last decade, or even probably longer, because before the early 2000s, the deep neural network itself has already been developed by a group of researchers, but it's not widely adopted. But after around 2000, 2003, 2005, when the handheld devices like mobile phones, smartphones are getting really popular, and people start sharing tons and tons of data. And that's one of the major driving factors for the explosion of the machine learning in the last decade. With tons of data and also the existing algorithms with deep neural network as a primary driving factor, and also the computing power. With all three major factors together, we see a very, very rapid growth of the machine learning and AI technologies. So the basic idea behind this technology is to get the data and started with some existing mathematical structure like a neural network, like the one I'm showing to the left here. Actually, it is a neural network. It's a multi-layer perceptron. It's a fully connected and dense layer neural network. There are many other similar neural networks or radically different neural networks, but they are doing something very similar, basically providing the mathematical structure to map your input to your output. So with that mathematical structure and some input data, you can train your model, and you get a mathematical model based on this structure trained, and you can use it. So now if you look at the whole workflow for the data-driven modeling, there's no governing questions there for you to explore, discretize, or writing mathematical equation, writing programs to do that. The machine will do all the dirty job, and just getting, all you need to do is just to get the input data and output, expected output data prepared for your model and pick the right neural network. And almost everything else is done now with very powerful frameworks like TensorFlow or PyTorch. And a lot of things could be done with those two frameworks without you dealing with all the detailed matrix multiplication and vector multiplication, etc. So those are done automatically nowadays. After your model is ready, you can take new data set and start make predictions. That's exactly what we wanted to do with traditional theory-driven model. We wanted to improve our model, our mathematical equations, adding terms, drop terms, and getting all the terms figured out. We figured out some mathematical, physical meaning for all the terms, and then we make predictions. We want to get better mathematical model ready. But now, with a data-driven model, that's not the case. We just need to figure out a better way to get the neural network prepared and get our data prepared. So it's more or less like if you look at the competing factor between data and theory. Actually, it's like a balance you play between data and theory. If you have more data, and less theoretical understanding of the particular application that you're interested in, you probably better off with a data-driven modeling effort. By taking some existing mathematical structure described by neural networks, you just plug in your data and you'll get a black box of predictor that will give you some desired results, even though you don't understand much about internal structure of this mathematical model, but it's working. That's a really practical way of thinking about this kind of solution. It's not something that gives us a very good understanding of how things work, but it gives us a very good mapping function for you to do something for real without spending years to figure out some mathematical equation behind it. So on the other side, you have some theory-driven model. You already know a lot of details about the application that you're looking to. For example, you're doing fluid dynamics simulations. Navier-Stokes equation is probably the one you want to spend a bit more time into it, and you learned a lot about numerical analysis, and a lot about instability stuff and boundary layer series. All those mathematical methods. You study this theory, and then you try to discretize it, and then you write a program and start solving your problem for it. So that's how the theory-driven model is working. But there is something in between. Actually, usually for people doing scientific computing, usually they don't pay much attention to this data assimilation. Actually, it's very useful in practice. Data assimilation is used a lot in, say, weather forecasting and climate modeling, weather, long-term, short-term weather forecasting, etc. So the basic idea actually is not that hard to understand. So you have a boundary equations, and you know that all the gas and fluid are following, say, Navier-Stokes equation or simplified Navier-Stokes equations. Then you have that mathematical model with you, even though the model itself probably already oversimplified. But you do have the help from all the different observation data sets, and you can observe the use a satellite image or some weather stations locally. You can just collect the data, and that observed data could be used to correct your model. So the basic workflow is more or less like you run your simulation with your theory-driven model. After a while, say 1 day or 2 days, or depending on how often you want to update your model, you take the observational data at certain locations, and you take your theoretical output at certain locations. You do the weighted average. The weight itself will be depending on the variance of the measurements. So there are many other factors you could put into. There are many ways to do the weighting, do the weighted average for the observational data and the theoretical data. And you can merge them in some way, just pull your solution back to the physical space. And then you continue evolving, with your theoretical driven model. And after a while, you do that again. So depending on how often you do it and how smoothly you want your output data will be, there are many ways to do that. So if you go to NCAR website, I have a link here. Oh, wait a second, I haven't shared. I'll send the link to everyone right after my presentation. I'll post it to the chat room. So if you click the link to, at the bottom here, I'll point you to a website and tells you a bit more about how this data assimilation is working. So scientific machine learning, I think is giving us the best of the two worlds. In many cases, when we're solving the real world applications, the theory-driven model itself is not sufficient to solve the realistic equations, to solve the realistic problems. In many cases, we don't have the knowledge about certain phenomena inside the physical system we are looking to, or the physical system is too complicated to be modeled with a simple model we might have. So there are, we on one side, we can continue, building theoretical models, but on the other side, we can start collecting data, whatever data we can from the system, from different perspectives. By joining together, with something similar to data assimilation, but we are trying to use the machine learning modeling, methodology built into our scientific computing methodology, and we can have a so-called scientific machine learning methodology. That's the scientific machine learning mostly about. We try to join hands with scientific theory-driven model and data-driven model. So there are three paradigms I think might be applied here. So first, I would call it feeding, in the sense that you have a theoretic model already there, but the initial condition that you want to fit into your model for study the different properties, different perspective of your application or your object will be require a lot of effort if you want to collect the data, doing all other things. So one solution is to build up a neural network machine learning model to help you to explore the parameter space by generating initial data, tons and tons of initial data for you to just fit into your theory-driven model, and then you can better explore the parameter space. And also the better in the sense that it's not only provide the machine learning model will not only provide the input data for you, but also find a way for you to do the searching. In a sense, when you're doing drug discovery, or when you're trying to explore the different kind of materials and study their properties, this is a very, very useful tool. You not only need to search, but you need to know which direction you want to search. So this kind of feeding will not just generating random input, but also give you a direction of the searching when you're exploring your parameter space or material space, whichever space you define here. So another paradigm that you can use scientific machine learning is to do so-called surrogating. So it's more or less like a replacing. You have a theory-driven model, and you want to build a machine learning model that can replace your theory-driven model. One of the main reasons that you want to do that is because the theory-driven model is too complex, and also is too computer intensive. For example, if some simulations will take you probably months and weeks and months to run, a machine learning model will be able to do this much shorter time. And the pins physically informing neural network that Levi will going to show us, it's actually, I think it's more or less along this line. So you have some physical models, we understand what things are working, and then we are trying to build up neural network to take the input data, boundary information, boundary data, and then we can feed into our neural network. We can completely replace your existing theory-driven model and give you the output. And this is very popular way of doing scientific machine learning, but it's not the only way. And as I mentioned, feeding is one way. They also use scientific machine learning to do the inverse problem and many other things. But replacing existing theory-driven model is actually a very, very popular and widely adopted approach now. That's mainly because the machines we are using nowadays is heavily GPU equipped, heavily equipped with GPUs, like the one we have at HPLC. The Grace supercomputer has 100 GPU nodes. Each one has two A100 GPU cards, and each GPU card contains 40 gigabytes of memory, which is not imaginable just several years ago, but now it's there. And those GPUs are much more efficient and faster, much faster than CPUs in many applications. And by leveraging this computing power and GPUs and using the neural network, that will be gradually simplify the way how the traditional solver is done. So it's like, I think it's a benefit of two. First, it's a benefit of the machine learning algorithm itself. Another benefit is the hardware. If I ask you to write a CUDA code to port your code on our GPUs, it will take you for a long while, and it's not easy. I was teaching a CUDA short course at PRC. I know, for simple, I usually highly recommend people to write their code using libraries, calling CUDA library, instead of writing your CUDA code directly, even though the performance might be better if you use CUDA. But by replacing your model with a machine learning model, it's more or less like calling a library, and you are already leveraging the GPUs directly and very, very efficiently. So that's another benefit that I can think of by surrogating your traditional model, theory-driven model with a machine learning model. So lastly, it's a listing, which is more complex, and I think it's also easily to understand, because when we try to solve some problems, it's not like we needed to replace a whole theory-driven model with a neural network. Only part of it might be very expensive, compute intensive, and we can just offload that part with a neural network and replace that part with a very efficient neural network, and then we can just offload it more or less like when you are doing run a simulation on a GPU cluster. Some part of the code you can offload it to GPU. It's in the same way. So for traditional machine, modeling, this is a diagram I took from my PhD thesis. And for those of you who have done the scientific machine learning, you should have some rough idea about what this diagram talk about. For those of you who don't understand, basically what I try to show here is that you start with some, physical problem at the very top, physics problem, hard problems, and then you try to find the mathematical models to describe your PDEs, to describe your physical problem. The PDEs are very, very commonly used way to describe, but it's not the only way. You can have ODEs, you can have geometric, algebraic equations even for your physical problems. But in general, for most of the engineering scientific problem, PDEs are the probably best one to use. Then you start to discretize your equation into algebraic equations, and then you put it into your, you write a program, C or Fortran or Python, whichever you prefer, and then start solve your equation and get the output. And in the process, you need to worry about convergence, discretization errors, etc., consistency, and there are a lot of things to consider if you want to do traditional scientific computing. But for data-driven model, it's much simpler in a way that you just need the data. As long as here we're talking about supervised learning mainly because we need an input and output to train our model, for our model to give you the mapping from the input to output. So whenever you're giving me some data, I should know what the output or your expected, what your expected output should be. Then I'll take both the input and output. I train my neural network and the function and give you a model. Model itself is just a function, more or less like a function. So the artificial neural network is basically doing a mapping from the, there is a biological inspiration. They have an input, output, you have multiple input, output, you have layers connecting each other, you have activation functions. So it's just like a neuron in the sense that it's give you the input and output. There are some process in between to process the information. So mathematically, you can write down all the equation in a nested function, like the one to the left here, where inside this xi could be written as x, previous layers xi. So you have a nested f, weighted average of this x, and which could be written as another weighted average of this another previous layers x, etc. So you have a nested function for multiple layers. Actually, the beauty about this kind of formulation is that everything you write down here, they are explicit. So you have by writing down your equation like this, you have an explicit equation, mathematical expression to map your input to your output. Even though you don't know for sure what all those weights, and you don't know at all what those weights and biases W and B's are, but with all the data, you can train your model to figure out what's the weights and W and B's to give you minimal error. So F here in the function, it's a so-called activation function. And what it does is basically give you the, introducing the linearity into this neural network, also give you so-called activation. In the sense, if the whichever inside is below a certain value, you don't activate this particular neuron in a sense, compared to the biological inspiration. But it means above a certain threshold, this output will be activated. It will be activated, and the signal will be sent to the next layer, etc. So the activation function is more or less, the shape is like S kind of shape in all of them, except for ReLU, which is widely used here. It's a very simple one. Whenever your x is less than 0, you set it to 0. When it's greater than 0, you set it to x. So the derivative of these functions are very easy to calculate, but the most popular one is the ReLU. And the derivative of the ReLU is just a step function, which is 0, below 0, and 1 when it's greater than 0. So this, even though it's a very simple function, but using this activate function, you can have a long linear function constructed to map your input to output, which actually one of the main reasons why this neural network is so expressive. And we'll talk a bit more about that in a second. So what you're training here, so you define after you define your input and output, this mapping as a function, you can calculate this a loss function, and which is more or less like error. Whatever error you define here, for different applications, you have different errors to define here. So the way to calculate the error the way to minimize this error when you train a model is use so-called gradient descent method. There are many variants of this method, but the basic idea is to take derivative of this loss function against this weight, which is a variable here. X and B, X and Y prime here. Those are the input. Those are the data set you have. Partial L, partial W will give you the gradient, and alpha here will be so-called the learning rate, determining how far you want, how big a stride you want to go backward to change your weights. So this gradient descent method will give you the sense of direction you want to change for your weights and biases, and also give you the stride you want to change. So by minimizing, by finding the right direction and the right stride, you can quickly get the minimum of your loss function. So that's a whole training process. Actually, it's more or less along this line. You want to find the right direction to do that. So deep neural network itself has been really successful in many applications. One of the main reasons is that it's actually a so-called universal approximate. So it's able to, some already prove it mathematically, saying that for most of the functions, or probably not all, I think for almost all the known functions, that you can find this function, this mapping function constructed with a neural network to map your input to output. So that's very important. But for scientific machine learning, the more important one is the so-called Pincus theorem. Pincus, I'm not sure it's a fully proved theorem or not. I haven't really looked into the theorem myself, but it seems to providing us the proof that not only the values of the functions, values of the data, input and output data, the values could be mapped with this neural network, but also the derivative. So which actually means that for any part of different equations, you can not only map the input and output values, but also the input and output derivatives, relevant derivatives, so that you can have this mapping to establish this equation for your derivatives. Partial differential equations, it's all constructed with the derivatives, second order, first order, and this theorem means that you can maintain the value. You can maintain this function to map your value and your derivatives. And that's why, that probably the reason why this is possible. Scientific learning is possible is because this theorem, shows us a proof, but it's the scientific learning is made possible through this mapping. So this is a simple workflow. If you look at it, you have define a function which could be nested. Any function, this is just one paradigm I just mentioned. You can have a nested, you have a surrogate model, you can have a feeding model. But here, consider you have a very complex nested function. Doesn't really matter, because when you write on this nested function, it's explicit function. You know the mathematical formula to give you to map your input to output. So you can define your loss function explicitly. Loss function here will be loss function of the collocation points inside your domain. plus some boundary points, input data points, etc. So you define everything all together as a loss function. Then you apply gradient descent, and then you minimize your error for your loss function. You build up your physics-informed neural network. So the key thing here is the nested function error. For whatever equation you want to solve, this nested function need to be constructed, and the loss function need to be constructed, and the gradient descent will all be done automatically with TensorFlow and other neural networks, depending on which framework you're in. So I'll skip this one, which will be a bit more detailed about how to do the backward propagation, minimize your error, etc. But the last slide here will be linked to the next talk, half an hour talk roughly, by Levi. And so for the physics neural network, we are trying to figure out the correct, the best definition for loss function here. So the way how we do it is that we define neural network as shown to the left, and then we map the input x, it could be multiple dimensions, x1, x2, x3, and the time to the operator, which operator corresponding to partial t, second derivative, and then we define this loss function as the loss of some collocation points that you randomly or have certain pattern you spread it around in your computational domain. You get the loss error, which is a residue of your equation at a certain point inside your computational domain, plus some physical regulations, which will be including your input and input data and initial data, and also will be relevant to your boundary data. So the loss here is defined as the sum of the residue plus whichever constraints you have with your initial condition, your boundary condition. And with that loss function, you can take derivatives of with regarding to a optimization parameter theta, and then you find your theta here, minimize your loss function by varying your theta. By doing that, you are getting approximator, universal approximator, then can map your input, whichever x1, x2, x3 t is, to your output u here. So with that, I'll probably take 5 minutes. I think I'm a little bit on 7 minutes over time. I'll be happy to answer your questions in the chat room. I'll let Levi to take the microphone. And Levi, do you want to share your screen?
Absolutely, I appreciate it.
Let me see if I stop sharing.
There we go. All right. Okay. Thanks, Dr. Chow. I appreciate the overview of scientific machine learning there. It's very helpful to kind of put into perspective what we're going to be discussing today. So as mentioned, this is going to be a discussion specifically on physics-informed neural networks, which was that last slide is discussed, and sort of the novelty of this. It was originally proposed back in the late 90s as a possible means of solving systems of partial differential equations, but back then, as with most deep learning problems, there just wasn't the compute power to solve it. And so it was recently revisited. So the field has been really rapidly advancing over the last 3 or so years. But that's because it was recently revisited by a group from Brown, and that's been gaining a lot of traction lately, and a lot of stuff has come out of that. So between that, and then there's another paper that came out called Neural Ordinary Differential Equations, NeurIPS 2017, actually won the best paper at NeurIPS 2017. That was also a big impact to the field. It's a little bit different flavor of scientific machine learning. We're not going to be covering that specific flavor as much today. But what we will be discussing was that last slide that Dr. Tao put up, which is sort of a collocation-based PDE solver that's built using a neural network, wherein you're approximating your solution to your partial differential equation system using a neural network and training that via a loss function that takes residuals into account, as well as explicit minimization of your initial condition and your boundary conditions. And so we'll get a little bit more into what that means here when we start digging into the code. I just wanted to provide a brief overview. We're going to go through this pretty quick and start digging into the code, because I know that's why most are here. So it's good to see that a lot of folks have a background in Python. The package is based in Python. For folks who come from other backgrounds, C, C++, Fortran, especially MATLAB, you know, the concepts are obviously very similar, programming language. So we should be able to, you know, kind of bridge a gap there a little bit. There's specific questions, we can address those as they come up. Once again, appreciate the opportunity to be here presenting today. So I'm Levi McClenny. I'm from the Department of Electrical and Computer Engineering. My research advisor is also with us today, Dr. Ulysses Braganetto, who I owe a lot to. I'm dual-hatted. I work obviously with the Department of Electrical Engineering, but I also am a ORAL journeyman with the United States Army Research Lab. So there's a lot of ARL and U.S. Army jargon on a lot of my slides because I've been working closely with them over the last couple of years in implementing some of these things and working with them. So I owe them a lot as well. So I have to give a shout out to Dr. Hiley at the Army Research Lab. I appreciate all the support. I don't know if he was able to join us today, but without him, none of this would be possible either. So a little bit of motivation. So there's a lot of software floating around out there for solving scientific machine learning algorithms. So current pin solvers, for the most part, are limited to single GPU. There are multi-GPU implementations out there, but we'll cover that here shortly. Typically limited to single GPU, sort of small problems, almost as a novelty of saying, hey, this stuff works, but you know, we're solving just really basic equations. And the idea behind this package was to take that and expand it a little bit and say, hey, we can really solve big systems or complex systems if we spread this out over in a multi-GPU environment and add some functionality to it to do that. Furthermore, a lot of existing software is based primarily in TensorFlow 1, and while effective and good at doing what it does, there's a lot of optimizations. The TensorFlow team is a lot of very bright engineers at Google, constantly releasing optimizations to the graphs that are being built by TensorFlow, hardware level accelerations, compiler level accelerations, graph level accelerations that are rapidly coming out in TensorFlow 2. And so we wanted to implement a TensorFlow 2 package that takes advantage of a lot of those things and simultaneously provides a good user interface for the user to go in and define their system, and then whatever their problem is, whether they're wanting to do a forward problem and solve a system of partial differential equations, or maybe do an inverse problem and solve for some parameters, an intuitive interface to do that. So we wanted the interface to read more like a mainstream PDE solver. So those that maybe work in Moose or other solvers like that, you know, where you go in and you define, you know, a system of modules, you define a PDE, a strong form PDE, and you say, these are my boundaries, and you just hit solve. That was kind of what we wanted to get to with TensorDiffEq, and the reason, one of the main motivations for building it is to make it a little bit more intuitive for engineers that maybe don't have as much of a programming background, but want to be able to solve systems of PDEs using pins to that an avenue by which they can do so. There are some, there is one specifically multi-GPU pin solver out there available through NVIDIA. It's not fully open source. You have to apply for access and do some other things. They actually just recently gave a presentation. It's extremely good software. But the idea here was that we were going to release a kind of a completely open source version of this, tailored to the community, allow the community to develop the software, as well as provide assistance, you know, with problems and things like that. So that was really what we wanted to get to. And while that software is extremely powerful, we were filling a different gap with the open source community, specifically in developing this software. So it is freely available on GitHub. We'll be discussing that here shortly. It's actually the first place we're going to go when we get into the code. So we'll see that here in just a second. So as I mentioned, our implementation is in TensorFlow 2. It takes advantage, or either it already or will be taking advantage of things like accelerated linear algebra, grappler for graph optimizations, as well as, like I said, there's a lot of compiler level optimizations that are coming out of the TensorFlow team to make these things faster and portable to be used on any type of architecture. If you're running on an Intel CPU, it'll optimize for that. If you're running on an ARM, it'll optimize for that. If you're doing it on the edge, it'll optimize for that. All of these different things are options with TensorFlow, and we wanted to be able to take advantage of a lot of that. And a lot of those things are coming out from the TensorFlow team, specifically in 2.0. So we wanted to build a software scheme that could take advantage of a lot of those things. And the other thing too is that the multi-GPU functionality in TensorFlow 2 is incredible. It's very intuitive and easy to use, and the TensorFlow team designed it that way. And that allows for us to get into multi-GPU training for large domains, problems that are difficult or where you'll need a lot of fidelity in the domain or things like that to capture different transitions and all sorts of potentially different dimensions. So a lot of, you can solve an n-dimensional problem with TensorDiffEq 3D and beyond if you're solving something that requires more than 3 dimensions. And so we really wanted to be able to provide a platform by which you could do things like that, where you're going to need maybe a little bit extra on the compute side because you have domains that are complex to solve and that are very large. So this is a brief overview of the interface. I'm not going to spend too much time on this because we're going to dig straight into this. This is actually one of the examples we're going to cover is the viscous-Burgers equation. It's got a shock term. And so we're going to go in. It's kind of a hard-ish problem to solve for, well, asterisk with current numerical solvers. It's actually somewhat easy, but we're going to go into that as a baseline example. So we'll cover a lot of this code in depth. So I'm not going to dig too much into it, but you can see here that, defining a domain, generating collocation points, defining an initial condition function. You go through and you define what your initial and your boundary conditions are. You append them to a list, and then you define a strong form of your PDE, what you want your neural network to look like, the layer sizes, and then you basically hit model.fit, and it trains your neural network. So we're going to actually see this in action here shortly. So like I said, I'm not going to dwell too much. I'm going to kind of blow past this. And so this is one of the examples we're going to work is the viscous-Burgers equation. So I'm excited to kind of get to that. Another example we're going to look at is something that we've been developing here locally, and we call it the self-adaptive pin. And it's been demonstrated to solve problems that the previous baseline pin were not capable of solving. So I think that's important to note as well. While there's a lot of excitement rolling around pins right now in scientific machine learning as a rule, it is not a one-size-fits-all problem. The baseline pin, the original formulation, does fail in a lot of instances. Whether that's failing because of the neural architecture, or it's failing because of something in the training, or it's training because of the solver. If you're using an atom optimizer with a specific learning rate, maybe that's not good for that problem. There's a lot of different things that could cause it to fail. It's a very open and rapidly advancing area of research for that reason. So one of the things that we've identified here at A&M and recently published a paper on is this self-adaptive pin where, for instance, this is an Allen-Kahn equation. And like I said, we're going to discuss this example specifically, where the baseline pin completely failed. Believe it or not, this is actually after training. So the exact solution is here in blue. So this is how it evolves over time. So this is taken at 0.25, 0.5, and 0.75. You can kind of see a 2D representation of the X versus T domain here. You see that it just, especially compared to the actual true solution, nowhere near the accurate, what the actual solution of this problem is. Using the self-adaptive pin, we were able to really closely approximate that. This is some modifications to the loss term. I'm not going to dig into a lot of specifics on that. We have the paper out, and I'll be happy to provide a link if anybody's interested in checking that out. But I'm going to go through and discuss how one could implement the self-adaptive pin. If perhaps the baseline pin is failing on your problem, then you can implement the self-adaptive pin with only a couple of changes to your code and see if that helps as well. So currently there's a lot of support in the package, and we are actively developing more and making it better, faster, and et cetera. So currently for domains, I say square domains. It's really just domains with you have a min and a max and as many dimensions as you need. So if you were to go in and do an irregular shaped domain or something to that effect, right now there's not support for that, but we're actively developing that direction. Specifically like the NVIDIA package, they model like a heart ventricle and that sort of thing. So we want to get to that point. Currently the software it doesn't support that right now, but there's ways of doing that, and we're looking that direction. Boundary conditions specifically supported Dirichlet. There's a function Dirichlet boundary condition, which we'll discuss. It implements periodic boundary conditions and Neumann boundary conditions. For initial conditions, you can do as many dimensions as you need to do. In the form of a function, you can represent that function as a Python function. So it can actually be a Boolean function. It can be anything that you can type into a Python function. So it's extremely powerful in that sense, where a traditional numerical solver may not be able to implement a Boolean initial condition. You can do that with this. Same thing on your, if you have a Dirichlet boundary condition, for instance, and you have some sort of Boolean Dirichlet boundary condition where above this value it's this and below this value it's this, you can implement that here too. So we have single GPU baseline and self-adaptive solvers. So the baseline pin is kind of the one that we kind of started this whole trajectory of scientific machine learning down the path that it is. And then the self-adaptive pin, like I said, is something we just put out in the last year. It has a multi-GPU baseline solver, so that's one of the cruxes of this, is that it can do multi-GPU training. We can provide transfer learning solutions. So for instance, if you only modify a single parameter, you have a solution already, you already solved your problem, but you modify a parameter just a little bit, you can go through and you can just transfer learn that pin to a different solution. And because it's built on top of TensorFlow and on top of Keras, any of the loss functions, and I should actually amend this to say any of the neural network architectures that exist in Keras are also supported by TensorDiffEq. Because it's built on top of those packages, it takes advantage of all of those features, which is really unique. And something else that kind of comes with us building it in Tensor 2.0 as opposed to TensorFlow 1, the integration with Keras and the integration with those neural network architectures is extremely powerful. It allows us to take advantage of a lot of those baseline features, such as just saving the weights of your neural network really easily. That's something that can be done in TensorDiffEq now without having to write any extra code. You just say, save weights, and it does it. And so it takes advantage of all of those things because it is a Keras neural network. You can use any type of method that usually will work on a Keras neural network. So that's an extremely unique feature we think of this package. Furthermore, something I'm going to cover, because I know a lot of, from looking at the survey at the beginning of this course, there's a lot of engineers that are in this from Arrow and Mean and all these other different places. So we'll cover some discovery stuff, because I think that there's going to be probably a pretty wide range of interest in being able to approximate parameters maybe from an actual solution. So you have data and you want to be able to isolate what a particular parameter value may be from that system. That's something that can be done using this package. So we call that, that inverse modeling piece or that discovery model piece. Right now, we don't have operator solving. So identifying like new physical laws is something that obviously we want to go. And it's the big dream of all sorts of people that are experimenting in scientific machine learning. But currently the implementation will allow you to do some parameter estimation. If you don't know the value of a constant, let's say in your PDE, you don't know the value of the elasticity or maybe something to that effect, and you want to be able to approximate that using the software, you can do so. And then data assimilation. So Dr. Tao talked about data assimilation and being able to say, hey, at this point, this is a snapshot of the evolution, and we want to roll that into the final solution. You can do that in this package as well. So specifically on the data assimilation today, I don't have an example built for that, but I'll show you the repository of existing notebooks. And I'll be working to add one into there soon that performs the data assimilation functions that TensorDiffEq has. So with that, we'll roll into the hands-on portion. And so it'd be probably a little easier if I was presenting on a screen and everybody was at a computer and was able to kind of follow. And so I'm going to share my screen, and I would just encourage you all to kind of follow along. If you do just want to watch, that's definitely an option. I'll send out some links in the chat so that you can kind of copy them down and maybe go back a little bit later to run some of these things for yourself. In the future, we want to be able to do this in Grace, and that is 100% the intent. For the time being, we're going to be rolling in a Jupyter Colab environment. And so we'll need to do some login and stuff like that. You'll be able to log in with your TAMINet ID. Probably most who have been working in Python are familiar with Jupyter notebooks and are probably familiar with Colab as well. So that's where we're going to start. So Dr. Tao, do we want to take a break here, or do we just want to roll in?
I think we can take a very short break, 5 or 10 minutes, and 5 minutes, let's say 5 minutes.
Yeah, that
and
sounds good. Yeah, absolutely.
We can stick around. Anyone, if anyone have any questions, feel free to ask us. You can just unmute yourself. We don't have a very big crowd here, so feel free to unmute yourself and ask questions directly.
To the chat.
So Levi, do you have all the links to the Jupyter notebooks somewhere?
Yeah, so I'll grab those real quick. So that was what I was I guess we can take this time to maybe get set up here.
Yes, it's recorded.
Yeah, so I think it is being recorded, right, Dr. Tao?
Yeah.
Okay. So to kind of get started, I'll find the link and I'll send it out. But this is everything is on GitHub. So if you just Google TensorDiffEq, it'll pop up with the repository. So this is actually the package repository while you're there. Shameless plug, while you're there, drop a star, and we can go down to, so this is where all the code actually lives. We discuss a little bit of the specifics here, and then the installation is actually covered in on the docs. So this is the actual baseline repository on GitHub, but the docs themselves live on TensorDiffEq.io, and the actual documentation is supported or exists on the website here. So let's send these out real quick. So this is a link to the documents. And then the repository itself, which I'll tell you what'll be more interesting. So on the TensorDiffEq repository, there's actually an organization called TensorDiffEq that kind of houses a lot of residual code, or houses the code itself for the package, as well as the source code for the website. And I have a notebooks file here, which is where I was kind of discussing earlier. We'll have things being posted here that are sort of like how-tos, written in Colab, and then in the future we'll be absolutely implementing these using Grace as a backend, which will actually make things go way faster too. So that'll be really great for the folks at Texas A&M that are doing research here. So this is really, as far as today is concerned, for the workshop, where we'll be getting a lot of the information, so we can follow along from here as well. All right, so I can, it's been a few minutes here. So if there's any questions, otherwise we can take off, or I'll be more than happy to answer any questions or concerns or comments.
Hi, cancel it. I think there's two of us are in the same room.
I've been there.
Yeah. Hi, can you hear me?
Yes. Hi.
Hello.
Hello.
I cannot hear. Okay, let me fix that. Sorry about that.
No problem.
No. Yeah, maybe I can use that.
Can you hear me?
Hi. So sorry, there are two of us in the same room, so that's why there's problems. So I was, we have this is a very interesting. This is very interesting, and I, in fact, talked to Jian. We have a nice problem for us to try out on solids, because I think it will be a nice contrast from the fluid problem, both for estimation of parameters as well as calculation of reflection. Is that something that we can try, or how do we go about it?
Yeah. So it is. So we'll go through and we'll run through some of the examples here, and we'll and especially in the parameter estimation example, for instance, and maybe that'll offer some clarity. And if not, we can exchange some emails. And
I would love to do that.
Yeah,
I think this is a great. I think this is a nice, no frills, clean version of. I know Karl is, so I've followed his work before, and this is a very clean version. I think I like this very much. I think this is quite fun. What and I want to really try out some solids problems, and
of course.
a good chance. Thank you.
Of course, yeah, absolutely, and that's kind of a standing offer for anybody who's interested in the workshop. I figure that most who are here today are here for a reason. They have a specific problem they're trying to solve, or maybe some are just generally interested in pins for a research problem. But we've been working with so far folks from the Department of Nuclear Engineering at Texas A&M, as well as kind of working intermittently with other places in electrical engineering as well. And so more than happy to sit down and have a conversation with, especially a little bit later on, so you can see some of the actual features of the code and what it's good at, what it's built for so far, and where it's going. Then we can 100% sit down and have a conversation about your problem. Yeah.
Thanks.
Of course. Yeah. All right. Any other questions before we dig into it? Okay, cool. All right, so let's get started here. So we're going to go ahead and I'm in an incognito session, so I should be kind of following through with what everybody else is seeing. If you operate in Colab, this will probably open up directly to the notebook. It will open up to the notebook if you're not logged in, but when you go and you try to actually execute something, it will tell you that you need to log in. So as you're doing this, you can go ahead and sign in. I'm just going to sign in using my not TAMU. And you can sign in using your TAMU ID, but you'll have to do the net ID process, etc. So after you log in, you'll be brought back to the page, and you'll be able to actually start executing some of the code. So as far as Google Collaboratory is concerned, so there are a few pretty unique features of Colab that we're going to take advantage of today that will 100% be available once we get Grace up and running, or how to execute the notebooks using Grace as a backend. And so really all of the code that you're seeing today will be able to be used with Grace. We just, once we get the notebooks up and running there. So I know that there's a lot of testing going on, and very optimistic that in the next few weeks, we should be able to get that going off the ground. But for the time being, we're going to run through Colab notebooks just so that everybody can see the code. So there's, for those who don't maybe know much about Colab, all of the code that you run in this notebook runs on Google servers. There's no data being exchanged between your computer and Google at all. It just runs and executes on Google's backend. So what that allows is GPU runtimes, because basically they spool up space available GPUs to use for Colab. So for the first thing, this is just sort of something unique and interesting to try. So if you go in and you hit change runtime type, this will drop down a menu here, and you can select GPU or TPU, or none is actually just executing on CPU. So for the sake of this, we'll run it on a GPU environment, and then later we'll actually go back and we'll change to CPU, and I will show you how the code has to change for a CPU. And I'll give you a little spoiler, the code doesn't have to change to run on CPU. And that's kind of one of the really unique and distinct features about TensorDiffEq, is that since it's built on top of TensorFlow, it takes advantage of all the TensorFlow nuts and bolts, as I mentioned. And one of those is that there's no change to the code whatsoever to change from running on CPU to GPU. Now, when you run on multi-GPU, things do have to change a little bit, but I've rolled a lot of that in, and it's a pretty intuitive change to actually be able to run in a multi-GPU environment. Unfortunately, today we won't be able to really demonstrate that, because running in a multi-GPU environment on Colab isn't possible. Once we get going in Grace, then we can start to do that. So stand by, stay tuned. We'll do another one of these later, maybe later in the summer or into the fall, where we can actually execute in a multi-GPU environment. So for the time being, we're up in the Colab environment, so you can actually check to see what kind of GPU you have. So if you're in here and you can type the bash, the bang command here in your cell to run a command line version, and you can just type in NVIDIA-SMI, and then you press Shift Enter to run, and it'll tell you it's not authored by Google, it was authored by me, so you can hit run anyway. And then it'll run that, and it'll show you what kind of GPU you have. And so there we go. And we can see here that we've been given a K80 for this instance. These GPU instances aren't persistent, so whatever you run, if you let it time out, it'll only spool for an hour or two, and then it'll kick you off. Or if you let it sit for like 10 or 15 minutes, it'll automatically log you off. And those instances aren't persistent. So whatever you run, if you run some stuff and you save and you get some output, you need to save it to maybe a Google Drive, like link your Google Drive to it in order to save it. So since this isn't specifically about Colab, I'm not going to dig too much more into the specifics of it, but just because we're going to be running in a GPU environment, it's kind of one of those unique features that I wanted to demonstrate. So we can see here that Google allows you to do all the CUDA versions and everything else. Once we get going in Grace, we're going to provide all the information as to how to get all the modules lined up. So you got CUDA and everything lined up so that you can run TensorFlow. Currently, the version of TensorFlow that's actually installed on Colab is 2.4, which I've been developing in the latest versions of TensorFlow. You got to be careful about rolling in too new features, because then people who are running in 2.2, 2.3 on a legacy system maybe not be able to take advantage of some of those new like XLA optimizations and things like that. So we've been kind of waiting a little bit to add new features as the new TensorFlow versions come out, to make sure that we don't outrun legacy versions of software maybe that are still running TensorFlow 2.1, 2.2. So with that being said, TensorFlow is hosted on pip. So all you got to do is run a pip install. So once again, using the bash, the bang here up front, you can just pip install TensorDiffEq, and it'll go through a install process, right? So it'll go through and it'll install and make sure that it's running all of the required dependencies. So this is just everything that it takes to download. And you just want to check on the bottom here, successfully installed, and it'll list you a couple of packages, but the last one here is TensorDiffEq. Currently we're on 0.1.9, and those are advancing. I've been pushing, every couple of days, pushing the updates that I have. So is everybody kind of up to speed with me now, or do I need to slow down a little bit? Looking good. Okay, all right, I will keep on driving. Okay, so with that, we'll have some imports. So since most people, it seemed like, came from a Python background, I'm not going to belabor the Python specifics about this. So if you install TensorDiffEq, you have to import TensorDiffEq. So for maybe those that don't come from a Python background, you install the package, and then you also have to import it into your session, similar to libraries in C, C++, that sort of thing. So the imports that we're going to use specifically for this viscous burgers equation example, which I showed in the slides. So I guess to show the answer to the test, we're going to be implementing this specific example as a baseline, kind of a hello world. This is actually an example that's in the original PINs, I say the original PINs paper from 2017 by Perdicaris and Raisi. So this is going to be implementing that version just to kind of show and demonstrate some of the baseline capabilities of the code. And this is going to implement the baseline PIN, the very basic version. Okay, so getting into some of the specifics of the code and what's required to run, to solve, in this case, a forward problem. We're going to solve a system of partial differential equations. Specifically, the system that we're looking to solve, now that we've got everything installed, is going to be this viscous Burgers equation. We have a shock term, so we have the Burgers equation here. We have it sort of set up in a strong form where it's equal to 0, and we want that to be equal to 0 because we're trying to minimize the residual. A very similar way that you would be doing with, using traditional numerical methods. You just want to minimize that residual instead of using a test function or something like that, like you would in a traditional variational method. You're just doing it now using a neural network. So the problem we're implementing here, this is the actual strong form of the PDE. We're solving across this domain. X is -1 to 1, t is 0 to 1. And we have an initial condition here. It's negative sign of pi x. Sorry, just a second. The first paper proposing pins, I will find it later. And it was by Lagares in 1998. And then the most recent one, sorry, I'm answering a question in the chat, by the way. The most recent one was Perdicaris and Raisi. So I'll pull that one up here. Yeah, so let's see. This is his GitHub, but I want to find the paper. So here he has a website built that kind of discusses a lot of these things, and you can see we're going to be implementing. So this is the exact problem that we're looking at today. So this was in his paper. So I can send this link out in the chat. This is a high-level overview. They have a couple of journal papers out as well. And you can go there and find those as well. They're in here. I think in the citations of this repository, these couple of links here. So there's a couple of archive preprints, yeah, as well as this JCP paper. So these are the papers that started us down the trail that we are. The original paper from 1998 is Lagares, and I think it was like something to this effect. Yeah, here we go. Yeah, there we go. Yeah, that wasn't that hard to find. Awesome, good. So that's the original paper from 97 that kind of discusses this concept. Okay, cool. So back to the code. All right, so this is, yeah, so picking this back up, so the initial condition is this negative sign of pi x, and then we have a Dirichlet boundary condition where we're imposing we want to impose a boundary of 0 on -1 and 1, the upper and the lower boundaries of x across all t. All right. So we're going to go through and discuss kind of how to implement that in the code here. So first thing, since we have only an x and a t domain, we define a domain ind object, and this is exactly what it sounds like. It's an ind domain. And so all you have to do when you go in here and you build it is you just say, I have an x, and if you were to have a y, maybe if you were to have a z, you could just go through and define as many dimensions as you need. So I have an x, y, z. If I have a 3-dimensional problem, let's say, I can define x, y, z, and t. And as long as I dictate that the time variable in this case is t, then it'll know that. So for our problem, since we only have this 1-dimensional problem, we'll leave it as x and t. But in a similar fashion down here, if you were to have x, y, z, etc., then you could just go through and you can add the same thing. So I would just add my x, my y, my z. Now this isn't limited to 3-dimensional problems, right? So let's say if you're trying to solve a Black-Scholes method or something to that effect, and you're wanting to optimize your hedge fund cryptocurrency portfolio, right? So let's say I got my Doge in here, and I've got my I don't know, my Bitcoin and all these others, and I want to be able to build this high-dimensional system of stocks to optimize my Navier-Stokes equation, let's say. You can go through and all of those are dimensions and you can add as many of those as you need. Now, needless to say, there's a computational cost associated, but the point to this is that it's an n-dimensional domain, meaning that you can add as many dimensions as you need to, so long as you can implement the correct boundary conditions and things like that. So as far as solving a large dimensional problem like that, I don't have an example built. I haven't really gone through the process of executing, like for instance, solving a Black-Scholes with 20, 30 different types of stocks, that sort of thing. But it's something that the package is designed to do. We really built it around solving microstructure informatics problems, but lately have been using it to solve kind of all sorts of different problems. We've been working in heat conduction recently, some stuff in electromagnetics, so it's a universal package. It was kind of designed though to solve numerical or materials informatics problems, and so that kind of is where we get the three-dimensional, with time sorts of domains that we kind of focus primarily on. So once you define your domain here, you can go through and you just, in this case, hit shift enter, and it will bring in that domain, and that's it. So we've defined it. So all you're doing here, you define your X and your T. So you're just saying that those are the only variables that are in my domain. Those need to be defined as strings. And then you say that I'm going to add my X domain. I'm going to define what that is. It's on the beginning and end is -1 to 1, and it's got 256 steps in between. So the fidelity of that domain is 256 steps. Do the same thing with T. Now, it's important to note here that this is a meshless solver. So actually, really all that you're doing when you define this is you're not defining a 2D mesh of a 2D square mesh, where you have explicit squares that go all the way through, and this is the fidelity of those squares. You're actually just really all you're doing there is you're defining the boundaries, and you're saying these are all the points along the boundary that I want you to solve. But inside of the -1 to 1 here and the 0 to 1, inside of that domain, you're going to sample a bunch of collocation points for the pin to actually train. So in the next step, you just define how many of those collocation points you want to sample, and you say generate collocation points, and that's all it is. It's stored in the domain object, and then later on you'll pass the domain object into the solver, and you don't have to worry about any of it. Currently, the domain, the collocation point sampling is done via Latin hypercube sampling, but you can kind of modify that. It's actually a parameter that you can change a little later on. I haven't really added much as far as like changing that. Latin hypercube seems to be kind of the way to go for the time being, but there's of course other conversations to be had about sampling inside of your domain to make sure that you cover sufficiently all of the different nooks and crannies. Okay, so we have collocation point solved. So now we're going to define the initial condition. So we know that the initial condition from the problem definition is this negative sign of pi x. So now we just need to solve that as a Python function, or to define that as a Python function. So all that would be is this, you can use NumPy to do it. So you just define the sign of x times math. You got to use the math to actually get a pi definition. So math times pi. So now this is where I was going earlier, and what I was saying is that you can kind of implement whatever type of function you want this to be, which makes it, I think, personally pretty powerful. So you could implement a Boolean function here. So on your initial condition, if x is less than 0.5, you can say I want to return 1.0, else return 0. You can implement a Boolean condition on your initial domain if you wanted to do that. Above it's this, below it's this, or something to that effect. You can make that as piecewise as you want. And one of the unique features of TensorDiffEq is that it's not reliant necessarily on continuity in any particular place, because you're using a neural network to approximate it. It doesn't have any continuity requirements that maybe would be required in a traditional solver for the theoretical guarantees. Since this is a neural network-based solver, doesn't have the same requirements there. So you can implement this. Now, from a theoretical perspective, does it make sense? Is it useful? These kinds of questions still need to be answered, but you can implement this in the solver, and the solver will train. So for the sake of this question, or the sake of this problem, we'll leave it as what the problem definition was, which is just negative sign of pi x. So we'll run that. And that defines our initial condition function. To actually implement the initial condition and the boundary conditions, you define those. So we have objects in here, initial conditions, boundary conditions, in this case, Dirichlet boundary conditions as discussed. And so you can define all of those. My upper x is this Dirichlet where I want the value to be 0. It works on the x variable, and it works on the upper part of that domain. So you just go through and you specify that. And you do the same thing on the lower. Now, if you were to have a two-dimensional problem, and I have a two-dimensional example that I hope I have time to get to a little later today, you could go through and you can change this and you can make this function if you have an X and a Y, right? So you have a two-dimensional problem, you do X and Y, and then in this case, you would just add in, you would just add in the extra term here to, reflect your function of X and Y. So I'm not going to do that for the sake of time. And then you would just modify this to have, instead of just X, it would be X and Y. Okay. So I'm going to take a second there and I'm going to pause. So I've defined all my boundary conditions at this point and my initial condition. And then we're going to get into the model definition here shortly for the PDE system. I'm just going to take a second there and answer any questions. Unfortunately, since I can't see everybody, I can't read the room and just, decide what a good time to stop and not is. So if there's any questions, please let me know.
Levi?
Hey, Chuck.
I don't, can you repeat what are those fidelity numbers when you add the domains?
Sure. Yeah, so whenever you go through and you solve the boundary, you need a certain number of points along the boundary that aren't sampled via collocation or that aren't sampled via Latin hypercube. So what basically you're doing is you're saying there's this many points along the X boundary that I want to be able to sample from, and we sample from those. So when you build that, I just don't want it to be conceived as like an actual mesh, because it's not an actual mesh like you would use in a finite element solver. All you're doing is saying that the fidelity on the domain is this, and the X domain is this, the T domain is this, and it's maybe broken up 100 times. And then whenever the solver actually goes through, it generates all the possible combinations of those 256 by 100 points to solve along the boundaries whenever it goes through and solves the boundary conditions.
I see. Thanks.
Of course. Any other questions there?
Why, this is a Jian. So for the direct light boundary condition here, you have a target which is upper and lower, which is very, very specific. How about you? What if you're dealing with 3D? And if you don't have the sense of upper, lower, and arbitrary boundary condition, how will you deal with them?
Yeah, that's a great question. So in a 3D problem, so if you were to take this and expand it into 3D, so just I kind of picture a 3D problem as being, you define that you have a -1 to 1 in your X and a -1 to 1 in your Y and a -1 to 1 in your Z. And you know what those boundary conditions would need to be at -1 and 1, even in the Z plane. So that was the way it was kind of built. It's not designed for situations necessarily where you don't know what the boundary condition would be at the upper or the lower. And in that case, if you don't know what the boundary condition is, then it would, I don't know how to solve that even in a.
I'm saying probably for an arbitrary defined, irregular. I'm not sure if there are always lower and upper. Yes, but
no, that's correct. So this is that you're correct. So this is one of those things that once we get to a point where we're looking at irregularly shaped domains, there's some semantics of this that's going to have to change a little bit. And when that time comes, we'll be making those modifications. So what you're saying is absolutely correct. This wouldn't handle an irregularly shaped domain. If you had an L-shaped domain or something to that effect. So this is kind of for solving problems that exist in 1, 2, or 3 dimensions where there's a, kind of like I say, a linear span of X, Y, and Z. But if you had an irregularly shaped boundary, like you're trying to do stress and strain on a, on a compressor, and you have that, whereas typically you'd have to do that using finite elements because you'd have a mesh that you'd build in Gmesh or something, and you would run that. Currently, the support just isn't there for that because of time and development. And to my knowledge, there's really not a lot out there that can handle domains of that irregularity yet.
Sure.
So unfortunately, that's a future work problem. But that's kind of the state of a lot of where pin solvers are is, we can solve these domains that we've been working in, and then, we're going to continue to move the direction of irregularly shaped domains such as that.
Okay.
Does that answer your question?
Yes. Thank you.
Absolutely. Okay. Any other before I continue? All right, great. Okay, so the solver expects these boundary conditions as a list, and it iterates through that list whenever it solves to find all of its different loss terms. So you just simply append the initial here, the upper and the lower to a list. So we'll do that. and we'll call that BCs. So now kind of gets to the meat of how you solve or how you define your PDE system. And
does the order matter here?
No. As long as it's in there, it'll find it. The order doesn't matter. And you know, of course, if you had a Y, you would include your upper Y. You know, that sort of thing. Now, if you have a periodic boundary condition, we'll get into one that shows a periodic boundary condition where you won't have an upper and a lower, for instance, right? So that's one example where you won't need this target is upper, target is lower. So this, just because this is a really simple example, we kind of really explicitly define these things. There's also a function Dirichlet boundary condition where this is kind of a really limited thing. You can only define it to be like a value of 1 or point of 0 or whatever. We have a function Dirichlet boundary condition wherein you can find a Dirichlet boundary condition that's sort of a more true to the definition boundary, where you can actually define a function such as, you know, sine or something on an upper and a lower domain. So that's supported, that's in the documentation. I don't have an example that has that built, but that's something that we support, is if you need to implement a sine wave on the upper, on the upper boundary of your X or whatever it may be, you can do that. And we have Neumann boundary conditions that do the same thing. So you can also define the flux at a boundary as well. And same thing there. The order in which they're fed in doesn't matter there either. Okay, so when it comes to defining your PDE, your strong form PDE, you kind of write it out in plain English. And this is one of those things that we were kind of trying to get at with the interface. And so you need to first pass in your U model, which is your neural network model. So you define this, or excuse me, your first term needs to be this U model term. It's built in the solver, but you have to add it in as an argument to your function. It's just part of the syntax of the package. So if you take this general kind of framework, this boilerplate little method right here, and you say, okay, cool, I have an X in mine, but maybe I have a Y and maybe I have a Z, and then my neural network is a 3-dimensional, 4-dimensional, I guess, with time neural network. You know, you can just modify the code to incorporate all of those inputs, and then you would just concatenate all of those as they go in, X, Y, and Z. Just like that. And I do have a 2-dimensional example a little bit later that will kind of massage and maybe solidify some of these things. So you'll run in and you'll go in here, and your U model is a neural network model. So like I said, this is just some code that has to kind of be in there, but it allows you to define what specifically goes into that neural network, and you concatenate the X and the T. Because it's a 2-dimensional. In this case, we have a 2-dimensional problem. Our neural network, the input layer is 2, because it's just dimensional, whatever the dimensions of the problem is, of the input to the neural net, because you're trying to approximate that solution based on, you know, all the different combinations of the input domain. So in this case, you just concatenate that together, and you feed it as your input to your U model. Once again, you don't hard define this prior to. So you'll notice that we don't define a U model anywhere up here. The solver does that for you. Like I said, you just have to pass it in as an input to the function. So that's something that just has to be in there. The rest of this, X, Y, etc., can change around. So since we only have X and T, I'm going to fix that and leave it as X and T before I break and confuse myself. So then you define your gradients of your partial differential equation just in terms of this TensorFlow.gradients function. So this, Dr. Tao skipped the slide on automatic differentiation for time reasons, but this implements that automatic differentiation that TensorFlow is designed to do. So TensorFlow is kind of what conceived as this, you know, neural network solving package, and that's true, but really what it does is implement automatic differentiation really efficiently. And we're taking advantage of some of the automatic differentiation primitives in TensorFlow that are used typically to solve neural networks, but we're kind of using them for a slightly different application, which is to take derivatives of a neural network with respect to its inputs. And that's exactly what you need to do when you're defining a strong form of a PDE. So in this case, we have the first derivative of U with respect to X, of the neural network with respect to X. And then we take the second derivative, since we need that second order term. And then we have the derivative with respect to time. So we do the same thing there. And then we define the strong form of our PDE just in code, in plain English. U sub t plus U times U sub X minus this constant term here, 0.01 divided by pi, times the second order term. And then you return that value. And that's the same way you'll define any PDE system. And if you were to have a coupled system, for instance, if you were to want to implement, you know, where you have another PDE system that has that defines a component of a second PDE system, you can do that using the exact same syntax. And so you would call it, maybe instead of F model, you would call it, you know, I don't know, G model, right? And we'll call it that. And you would take the exact same syntax, and it maybe takes in X and T. And then you can say that it's a slightly different variation of this where, you know, it's like, let's just call it, and I'm making this up as I go here, but it's just this, you know, we'll call it that, and we'll return that. Oops, G model. And then if you were to want to implement this, you would just say, let's say that instead of this U sub X term being here, I want to use my G model. And I would just pass in the exact same variables, right? So that's how I would implement a couple of PDE. So it would return my F value here. It would return the value that I'm interested in from this system. And it would take it and it would run it into this system. And then that would be the actual final output that I would feed into the neural network, or into the solver. So that's how I would implement a coupled system. Okay, so in this instance, that's not true. So let me just go back and Control Z my way to something that works here. Okay. Okay, so with that, I'm going to do out my F model defined, which is just my function model that I've got, you know, part of my problem definition up here. And then I define my layer sizes. So this is what actually defines your fully connected neural network. And we'll get into some advanced features here a little bit later of how to maybe modify this to take advantage of some of the nuances of Keras. So you can implement things like batch norm, some other things like that into your neural network that are all of that just works because it's all built in TensorFlow and Keras. So you can implement batch norm, you can implement some of those things. You could even implement things like CNNs and RNNs, but you would have to, you could do that in Keras. Doing it in the package would be a little tough because it's not really designed for those, because that would kind of fundamentally change the way that your neural network is training and what it's doing. But you can implement those things because it's all built in Keras, and you can define any Keras neural network and change that internally to be what the neural network that you define in Keras syntax and maybe sequential syntax is. So in this case, we'll define a regular fully connected layer. It has 1, 2, 3, 4, 5, 6, 7 layers. The important thing to note here is that your input dimension is 2 because we have X and T, right? If this was maybe a XYZ T domain, then we would have the input layer would be 4, right? And then your output is 1 in this case because you're only trying to approximate the U solution. So you only have 1 output for every X and T pair, right? So there are instances where, for instance, if you're maybe solving a Schrodinger's equation and you have a real and an imaginary component, or you know, that sort of thing, where you could amend that to be a dimensional output of 2. Currently, we're working to roll some of that support into here. So that's something that is a future work thing for the package, but I'm actively working on being able to do a little bit more than just kind of this basic like output of the U network, where you can do maybe some real and imaginary type estimation using the package. Okay, so the layer sizes are in there. So now we're going to kind of get into the meat. We're just going to run the solver. So you define this collocation solver in D. So that's the in-dimensional collocation pin solver that we've kind of been talking about, that we talked about earlier in the slides. That goes through and performs the residual-based loss minimization, as well as the hard solving of the boundary conditions. Inside of the, so you call the model, you initialize the model, you say .compile, call the compile function on it, and you pass into that the layer sizes, which you just defined here, the model that you built, your strong form model, the domain that you defined up earlier, and then the boundary condition list that you defined earlier as well. And then from there, you hit model.fit and you run, in this case, we'll run just 2000 TensorFlow iterations and 2000 Newton iterations, and you can kind of see it work. So it'll drop off this fancy, you know, this fancy little banner here and spit out your neural network shape. And then you can see here it's training. So it's a little laggy on Colab, and I think that just has to do with the Colab in the back end and it talking back and forth. If you run this on in a bash environment, if you run it on command line, this is a lot more, it's a lot less, well, laggy. So you can see it here as it's training. So that was 2000 iterations, even on a K80 GPU took 27 seconds. So it's reasonably quick on GPU. This is for 10,000 colocation points. So this is essentially implementing the same problem from the Raisi Perdicaris paper in the same scope, the same time, or the same size of problem. And it does it here in this case will be approximately 3 minutes. So the LBFGS iteration training takes a little bit longer just because it has to do a lot more gradient work there. This is also implemented in eager mode. The eager mode, I do have a graph mode implementation of this. And it is fast compared to running it on your laptop. That is true. So that was something I was going to go back and demonstrate here in a second, Dr. Braganetto. So this is just with a K80 GPU. So the other thing to put this in perspective as well is once we run this on Grace, A100 GPUs are about twice as fast as K80s. K80 GPUs are 7-8 years old now. I'm not 100% sure. So it'll be remarkably faster.
Levi, do you want to explain a bit about the eager mode and also the computational graph? I believe some of the attendees might not understand them.
Yeah, apologies. That's a great point. Thank you for that. So in TensorFlow, especially in TensorFlow 2, originally in TensorFlow 1, everything was built into a computational graph. So you had to define that graph of saying this is connected to this is connected to this, and now run. So you had to define your entire computational graph in terms of what the hard mathematical operations were going all the way through. So now they provided a lot of a very intuitive interface to do that with. So you could define layers in TensorFlow, and Keras was the original version of Keras was built on top of that. But it still required you to go in, and for those who maybe built in the first version of TensorFlow, you had to define placeholder variables, you had to build a session, and you had to run things through it. And it worked really well. It was very fast. It was kind of a little clunky, and the TensorFlow team sort of knew that. And whenever they released TensorFlow 2, they got rid of the you need to build a graph before you run code paradigm, and they changed it to what they called eager mode, which was a feature in TensorFlow 1. It did exist, but you had to enable it, and it made things a little bit easier to work with. And so the TensorFlow team decided that they were going to make that the primary mode of operation. The downside of eager mode is that it's slower because it doesn't build a graph before it runs. So what you can do in TensorFlow 2 is now you can build code that runs using kind of a more intuitive syntax. And you say, okay, now this runs. I'm going to build a graph out of this, and they offer a very unique, very easy to use process by which you can do that. So eager mode runs a little slower, is a little easier to work with, whereas graph mode runs significantly faster, but is slightly less intuitive when it comes to actually building out the graph and writing the code itself. However, for the sake of this, sort of distributional based software, in this case, we run pretty much everything in graph mode, unless in this particular instance, especially for a small problem, the LBFGS eager mode actually works a little faster. For bigger problems, the graph mode works faster. And this kind of gets into the other conversation that exists between CPU and GPU processing, where just because you run it on GPU doesn't necessarily mean it's going to run faster. The problem has to be optimized to do that. In this case, it does run significantly faster because there's a lot of operations that can be parallelized really easily, and TensorFlow does that by default. So because we're running 10,000, for instance, colocation points, it's a lot of colocation points. So for that sort of problem, there's a lot of rote computations done over and over and over that don't rely on each other. So it can all be done on GPU really easily, and the graph mode execution takes care of that and makes it run really quick. Okay, so we have our solution here. So we can see that the loss, so first we'll take a look at some of this. So this was running, it took 27 seconds to do the Atom training. And then the follow-on LBFGS training, so this is sort of one of those heuristics of training pins, is that the Atom training needs to be run first, or it has kind of been observed to need to be run first, because that gets the solution in the general ballpark of what it needs to be, but isn't very accurate because it's it's a stochastic gradient descent based method. So it's only as accurate as your learning rate will allow it to be. LBFGS is a lot more accurate of an optimizer and gets you down to a pretty good level of fidelity on the solution space. But if you start it using LBFGS, the solution space is just too large and it can't figure out exactly where to go. So Atom gets it in the ballpark, and then LBFGS kind of fine tunes it. And so if you look in Julia and that's the neuralpdes.jl package, that's actually, they used to just do LBFGS optimization, and they've changed all of their examples to reflect now Atom and then LBFGS, just because the training is more stable when you do it that way. kind of opens the door to a research question of like, what's the best optimizer? And this is a conversation we've been having actively amongst our group of like, how do we better fine tune optimizers for this? So
I think this is also comparable to the warming up stage when you're doing mental color simulations.
Yeah.
You really run warming up stage, probably 1,000, 2,000 iterations, and then you start running your mental color simulation. It's very.
Yes, that is exactly what it is. And so yeah, if you need to leave, you can go to the Collab notebooks and you can run through them on your own, and you can see the other examples we're going to cover a little bit later too. So thanks for coming, thanks for attending. Okay, so to compare the solution, so we can see here we have a pretty good loss, a pretty low loss, right? We see that this ran in 27 seconds. The Atom runs really quickly because TensorFlow is designed to do that. LBFGS TensorFlow doesn't exactly have a built-in function for it. It used to, now it doesn't. It changed with TensorFlow 2. So this is actually an implementation that was built with LBFGS. It's a little bit slower. And it took about 3 minutes to run 2,000 iterations. So you can see here in the span of less than 5 minutes, we were able to train that, and that was on GPU. So now what we're going to do is compare the solution we just got to the actual, to a high fidelity solution to see what the error is. So you can simulate, needless to say, the Viscous-Burgers equation using a finite difference solver, finite element solver. And so we'll download some high fidelity solution data. So this is hosted on my GitHub. So this is a bash command to just download that. And then we'll import it and we'll take a look at how the solution compares to the actual solution that we get from the high fidelity finite elements finite differences solver. So in this case, you can see that even with just 2,000 iterations of both, the L2 error is what is that, 0.05%, and you can see here that maybe a little hard to see across the screen there, but the solution is extremely accurate. And so if you're following along, you probably can see a little better on your own screen. But yeah, this is sort of a get your feet wet example to implement some of the code, or to implement some of the examples that have been floating around in the literature. So with that, I'll take a brief second to discuss. So this is a full example. I went pretty slow on this one just to kind of hit on all the pieces. We'll go to the next one and it'll be a little quicker, and I'll kind of just more so explain the differences. But I'm going to set something up here and I will demonstrate something real quick. But in the meantime, does anybody have any questions about this example and some of the implementation?
Levi, just one quick question. You showed an example that we have one PDE, so we have one residual equation. In the case that we may have two PDEs, and because of these two residual equations, is it possible to use the package?
Yeah, absolutely. So if you have two PDE systems, it was kind of what I was describing here, where you would define, are they dependent upon each other? So is one feeding into another, or are they just independent?
No, they are independent.
Yeah, so that would require maybe some modification on to the code a little bit. It's definitely feasible, because all you would have to do is add another term to the loss to do that. But it's definitely feasible. Currently, maybe not supported, but it could be a potentially easy addition. So if you'd like,
I'm just thinking something similar. So you can simply add two equations together, treat it as one equation, and then you feed it into your current model. Should be working.
Yeah, you could. That's true. You could potentially do that as well. Yeah, and so
but in this case, if we put it together, you will have only one loss function term, and this maybe you have some problems. One going another direction. One going in one direction, the other go in the other direction. It's better to have them decoupled to treat it correctly, I think.
Yeah, and that change could be reasonably straightforward to implement to add that feature. And so if you like, we can maybe exchange a couple emails and have a conversation about it, and then potentially add that as a feature. I think that would be good.
So this would be a matter of having two outputs, right? And then two outputs, one for each response, and then you can code the two PDEs in the loss functions. I mean, I think that's how you do it. Is that right, Levi? I mean, two outputs.
Yeah, you can do two outputs in here. That's something that is possible. I'm curious. So Marcelo, can you comment on that? You DM'd me here, but can you comment on? You say you did that. How did you do that?
Hi, Levi. I have worked on your code for the last week, and I have implemented these two residuals. So what I did, I went to your code, inside your code. When you have one residual, if it's a tuple, because your code is going to be a tuple, then I just did a loop. We can discuss after, but you can now, the way I did, you have two residuals, and you can have two weights, separate weights for each one of them. And then you can also implement the self-adaptive to your code. But it's really simple, just one or two lines of code.
I see. So you split it and you ran a loop between the two. Yeah. Okay. So regardless, it was a modification of the baseline code. So we should circle back to that. And I kind of like the last suggestion that you had. I would encourage you to maybe open a PR if it works, and it works in the single residual case and the multi-residual case. Then we can open a PR and just add that in as a feature.
Okay.
We can also have a conversation offline a little bit more too. So it's an interesting thing that I hadn't previously thought about. So I like the idea of doing that. So,
Levi, quick question. This is Eduardo speaking. Thanks for the presentation. Just a quick question. We can talk offline. I mean, if time permits. But have you done any sensitivity in this particular case, the Burger's equation? What happens if you have a very, very small diffusion coefficient?
I haven't run that. I haven't built it, but that's definitely something that could be. So this is a modification to the actual system itself, right?
If you go to your equation, the coefficient 0.01.
Yeah.
Can you try just a 10 to the minus 6, let's say?
Yeah, you can. Yeah, absolutely, and run it. Now, I don't know what the results are going to be. I haven't run that myself, but it's definitely something that you could change really easily here. Just
Okay.
Yeah, that would just be. I think it's one too many. So 1 to the negative 6, you said, right? So I think that's right.
I'm just looking at some sensitivity to this number, because what happens in our case, and what Marcelo and Emilio is working on, is exactly this equation without that diffusion term, which means that it's a hyperbolic nature and cause lots of trouble.
Okay, so does the solver not work very well when you do that?
No, it doesn't. So I don't know if they try to use very small, in this case, very small coefficient. I'm just asking out of the blue if you have ever tried that.
I haven't personally. I've been kind of focusing on building out the features and stuff. I would love to have a chat with y'all specifically on what you're working on, because it sounds like you guys got some really cool stuff going on. I think we should.
Right. Yeah. So as I said, we can talk offline so that you can proceed.
For sure.
Thanks.
We should definitely do that. Okay, cool. So with that, so we have an example here, baseline example, and we've shown that, this is just the baseline pin and it works pretty well. So looking at the time, I'm going to run into the
Levi.
Yes.
So here, what you did is you trained the model, and now you can plot the solution on a grid. So you define the grid.
You're talking about
in the code, you define the grid.
Yes.
I mean, you can define any grid you want. And here define the grid.
Yep.
You uploaded the high fidelity solution, which is defined on a particular grid.
Yep.
And you just apply the model to that grid.
Yep. Model that predicts.
And it predicts the values, okay, on that grid. I mean, it could be any grid, right? I mean, once you have trained the model, I mean, it's just it's sort of like a model dot predict, right? You have
exactly.
Yeah. So that's a very good point. I mean, because like I said, it's mesh free.
Yeah.
I mean, it's completely mesh free. Once you have trained the model, I mean, you can apply it on any grid, on any mesh.
Absolutely. Yeah, so thank you. I did kind of just run that code and didn't even talk about it. So that's a very good point. So all this does is, like Dr. Braganetto said, it takes in the real data, extracts out the solution from it, and then builds out a mesh that does have finite points. Now, whenever this was solved using the high fidelity solution, it was solved on using a meshed method. So we just went through and essentially recreated that mesh, and then did a model.predict on that series, those combinations of X and T. So that's correct. And you could do model.predict on things that don't actually exist inside of that solution domain. It just hasn't trained for it, but you can hypothetically do that as well.
Yeah, extrapolation, right? You can do extrapolation.
Yeah,
Yeah, exactly. Absolutely.
You could do that as well. You could do that as well. So then all that it did was went through, and I have a find L2 error kind of helper function, and all it did was run that to show what that error was, and then ran some plotting functions that are built into the solver, or that are built into the package. So this is specifically kind of tailored to 1D with time problems. So if you, as you want to show a 2D problem with time, you can show a 2D problem that is steady state. But if you want to show a 2D with time, then it's a little bit more of a, you got to kind of go in and modify some of the things in here. But okay, cool. So any other comments on that? Thank you for that, Dr. Barrett. I didn't realize I kind of blew straight through that. Okay.
I think since you have 20 minutes left, you should, you know, maybe skip. Well, I mean, go maybe skip Helmholtz and.
Yeah, I'm gonna do.
Yeah.
I'm gonna do the parameter estimation problem. I think that
Yeah.
was more interesting to the group. So we do have the self-adaptive pin that's built to solve the Allen-Kahn problem. So just I'm not going to run the code necessarily. You can see in the example. So the Allen-Kahn problem is a different PDE system. The initial boundary is pretty similar to the last problem, but the main key difference here is that there's a periodic boundary condition which is built into this. So same kind of thing, import the package, define your domain. It's a very similar sort of structure to the last one where you have a one-dimensional X and T domain. And then, yeah, define your initial condition. In the periodic boundary condition, you can define your derivative model. So in this case, since it's only a 1D problem and we only wanted the first order derivative to match what the problem definition was, then that was all you needed to go down. But you can continue to actually add you know, derivatives. If you have a two-dimensional problem, for instance, then you would just have this UX, and you would change this UX to be, you would change this to be, you know, U or Y, and you could go through and you could do combinations of U and Y, right? So you want to output the gradients with respect to, you know, all the different dimensions that you have. In this case, since it's a 1D problem, not applicable, but if you work on a 2D problem or 3D problem, those periodic boundary conditions, you know, you want to make sure that those are actually continuous in all the different dimensions at the boundary. So that's something that the package is built and will support. It does slow it down to add those naturally, right? That adds levels of compute because there's more levels of gradients being taken, but it does solve that problem. And in this case, similar to what I discussed about last time, you only have the initial condition and the periodic boundary condition. So you just go through and you put those into your list. Same sort of story here. You define your strong form PDE using the TF gradients syntax. In this case, to use a self-adaptive solver, you do have to define the collocation weight variables and the U weight variables. So the self-adaptive pin, without getting super in the weeds in it, but basically allows, creates a vector of weights that are trainable that allow the solver to focus at different parts of the problem domain at different times. So if there's a lot of error at a particular point, the solver will pay more attention to it and drive that residual down. Or if it's maybe on the initial boundary, for instance, there's a really high error, it'll focus more weight on it and it'll drive that error lower via the neural network. And so it's a like we call it self-adaptive, it's kind of exactly as the name demonstrate, or the name would suggest. In order to actually build that out, you have to define those vectors of weights. And so we define the variable here where you have a variable of in sub f is the number of collocation points. You define it at the top. So here in sub f is 10,000. So you have 10,000 collocation points. So you need a vector of weights that's 10,000 long. So that's what you do here. And then your initial condition weights, which is what these U weights are, is 512. That comes from the domain definition. So here, domain X is 512. So that's how many you need. And then you pass those in. This is the layer sizes definition. So here we create a list. And then in this case, the only modification is that you, to the last code, is when you call model.compile, you add in the isAdaptive flag, you pass in the collocation weights, you pass in the U weights, and same story, you hit solve. It goes through. So this is luckily already solved, so I can just show you the example. Because you can see here the times. So in this case, to solve 10,000 LBFGS, or sorry, Atom iterations, it takes about 2 minutes on the K80 instances on Colab. LBFGS. This is only 1,000 iterations, just to kind of fine tune it a little bit. Gives you about a minute and a half, and then we'll do the same thing where we load the high fidelity solution, and you can kind of see here that so 6% error, but that's because I only ran 1,000 iterations of LBFGS. In the paper, we run 10,000, and you get it down to like 0.00001 error. So it gets pretty accurate if you continue to run LBFGS, kind of as expected. The key there is to get it close using Atom, and then further refine it using LBFGS.
It's interesting to see how the solution evolves too. I mean, like when you run 1,000 iterations, then another 1,000, and you keep adding, and then you can see how the solution evolves. I mean, how it gets closer and closer to the solution, and you can do that easily too in TensorDiffEq, right? I mean, you can run for 1,000, you can check, you can check it out, and then you run again. I mean, you don't have to. You can hot start from the previous training.
Yeah,
is that correct?
Absolutely. You can hot start from the previous training. You got to be kind of careful about the learning rates. So once you get it down to a certain level of accuracy and you reintroduce a really high learning rate, it'll bounce around a lot. So there's kind of a structure to that. I do have a write-up on that on the actual on the website here of how to. It's kind of a transfer learning problem. Let's see, modification of Keras optimizers. So in this case, what you would have here is you would import it and you would change the optimizer to be a smaller level. But yes, it will work if you do that. Yes, you just have to bring that optimizer and kind of tier and step that down.
Right.
What's up, Marcelo?
Levi, one question. Are you planning to do a plot of the loss functions? Because I would like to see how the loss functions evolve on time.
You are 100% correct, and that's something that you're not the first to ask, and something I'm looking at adding for sure. In the not too distant future.
I actually already done on eager mode, but when I go to the graph, I don't know how to do in the graph mode. So
okay, we can take a look at it. We can take a look. I think.
Are you able to just directly use a TensorBoard for that? Because it's
so sort of, but you have to do a callback in TensorBoard. So you got to, because this is all kind of hand built in low level TensorFlow. That works in Keras if you just call it, but because we're not using the Keras solvers, the TensorBoard callbacks don't work out of the box. Okay. Something that I would still have to hand build. You could do it in TensorBoard, but you may at that point you may as well just kind of output it as its own object and just say, hey, all of your plots are in this, output log object.
Yeah, TensorBoard itself is pretty generic. Even PyTorch can just use TensorBoard for visualization. So as long as you save your training log file to a certain directory, and that's it. And you can we can think about it later on anyway.
Yeah, as long as you add the hooks, yes, but you have to hand build the hooks. What you're saying is true though, yes, but because this is built in low level TensorFlow, it's something that we have to add the hooks for. But you can do that. Sure. You can do that. Okay, so that's the Alan Kahn example. Only a couple more minutes here, so we'll discuss. So you can kind of see once you get the feel for how the different things are built in this, it's a very similar, kind of intuitive thing for once you start getting an idea for how the structure of the package works. So let me go back to, why are you doing that? There we go. All right, cool. So let's take a look at some parameter estimation, and I'll just punt Helmholtz. It's a 2D steady state problem. So if anybody who has the link here, feel free to go back and take a look at that on your own. You can see how to implement the 2D problem that I kind of discussed earlier and was implementing. So for parameter estimation, so in this case, we're going to take the same Alan Kahn problem that we just had, but instead of knowing what those parameters are, which we'll maybe revisit here, what those parameters actually were. So Alan Kahn. So here in this particular problem definition, we know that we have this 0.0001, and this is actually a 5 here and a 5 here, so you can kind of factor that 5 out and call it another constant. So in this case, what we're going to try to do this time around is actually estimate these parameters here. So let's say we don't know exactly what these are, and we want to learn that from the data. So we're going to work the inverse problem. We have the data, and now we want to learn what those parameters actually are. We won't be able to learn what the operators are. So we won't be able to say, for instance, it's a second order derivative, but we will be able to say, hey, that parameter there, that constant, I can identify what that is with a reasonable amount of accuracy. I'm not going to actually run this one because this takes a little bit of time. It takes about 20 minutes or so, even on GPU on a Colab environment, which is something I'm actually going to start looking at because I think we can get that time down a little bit more. So same sort of structure where you just pip install TensorDiffEq, needless to say. Go through and do your imports. The first thing you need to do if you're going to do a parameter estimation problem is define the parameters. So in this case, we have two variables that we want to estimate. So you have to define it a list of two different variables, tf.variables. You initialize these to whatever works. So there's kind of a hand wavy heuristic there where you have to, where to initialize those variables to is sort of an open conversation. I initialize them to 0. I've noticed that when I even try to initialize them like closer to what the actual value is, it sort of actually messes with the training and doesn't work as well. So initializing them to 0 works reasonably well. So I'm kind of leaving that for the sake of this example, but that's an open conversation if somebody wants to run that down and pursue what the best optimization is for a problem like this. It's definitely an open conversation and an open topic of research. So in this case, if you want to actually estimate the parameters, you define your function model in a very similar way. The only difference is that you'll notice this time we have a var variable here. Note the var's argument, right? So in this case, we need to pass in the parameters that we just described. So you're not going to pass it in directly. It's going to happen in the code. So you just need to have the var variable there, or that var input to the function there. And then C1, we say, is the first. So you know that you're passing in params. Your params has 2 entries to it. So you need to grab the first one for your C1 and the second one for your C2, okay? So when you pass that in, you don't actually have to pass params into this function. That happens inside the solver itself. So you just need to pass in this var variable. You can change it. It can even be named something different if you want it to. But the important thing is that you grab the C1, your constants out of that var, out of that params list, okay? And you just put them in the right place in the function. So you can see now, instead of having that 0.00001, I have C1 here, and then C2 times U cubed minus C2 times U. So I'm just building back out this problem definition using the constants that I defined. The difference is now we just don't know what those constants are. We built them using a TensorFlow variable. So in this case, needless to say, we need to import the data first. We're going data to numbers, right? We're going data to parameters. And then you define, so you have to define the grid that you're going to import. In this case, since the data that we have is built on a grid, we have to define that grid because we actually, essentially in this case, we're doing a supervised learning problem. So we have a bunch of outputs that we need to map the inputs to, and we're going to do that via this neural network, and we're going to learn those constants through that process. So we define the grid. We know what the data is because we generated the data, or we took the samples ourselves using some sort of experimental process or whatever it may be. And we want to feed that into the solver now. So in this case, all that we're doing is generating that mesh grid of data where we have, in this case, 512 by 200. So somewhere, whatever that adds out to being number of data points, 104,000 or something to that effect. And you go through and, and build that out. And build up all the possible combinations of X and T corresponding to those data points that you have. So this is a labeled supervised learning problem. You can do this using a self-adaptive solver. Still researching a little bit as to how effective that is. Sometimes it helps, sometimes it doesn't. So we're kind of identifying when to use and when to not. In this case, while I do have the collocation weights built into this, I don't actually put them into the solver. It works a little better in this particular instance without them. But I do have to define the layer sizes of the network. And one of the unique features of this is that while you're training this, you're learning the parameters. So the process learns the parameters, but it also, an output of it, a byproduct of it, is that it also learns the solution network itself as it's doing this. And so if you go through and you call it now, in this case, instead of collocation solver ND, we use the discovery model. That's what it's called in the software, is the discovery model. So worthwhile to go back up here. So whereas normally you would, from TensorFlow or TensorDiffEq.models, you would import collocation model ND, now you have to import the discovery model. And then go through and the problem definition, actually the compile function is pretty similar. The layer size is F model, and in this case you have your input grid that you're solving for. and the real solution data. And then the parameter vector that you defined earlier. So these are the parameters that you're trying to solve for. So in this case, this is a list of 2 different variables that you're trying to solve for. By default, the TensorDiffEq implements an atom optimizer with a learning rate of 0.05. This is just kind of goes to demonstrate how you can modify that. And there's a specific section on the docs. I'm not going to have time to get into it today of how you can kind of hack the software to change things like optimizers or to change things like neural networks. Or of course, if you download the code and you make the modifications in the code yourself, that's needless to say a great method of proceeding too. And then in this case, for this, you just have to run, and the only way to solve right now, we don't have LBFGS implemented in this. It kind of creates a little bit of an issue in backpropagating against 2 different things, because you have to backpropagate against the variables themselves that you're trying to train, and then you have to backpropagate against the neural network weights themselves as well. So that creates kind of an issue with LBFGS out of the box. So that's something that's still being added. But as you go through and you solve it, so you can kind of see here, you'll get the running discovery model for parameter estimation out of the output. And you can see that the output of the solver takes about 20 minutes even on GPU to run. So it's a slower process. Like I said, I'm not going to run it today. But the VAR's output, so you can see here that it's 9.9 to the -5th, which is extremely close to the 1 to the -4th that we started with, right? And then 4.94, and we were shooting for 5.0. So you can see that it gets pretty precise after 10,000 iterations of training that data, of training against the Alencon data that we want to learn from. So circling back to the previous examples, it's important to note that there is no data that goes into the forward solving of the problems. So if you solve the Alencon problem in this case, right? So going back to this even in the self-adaptive context, no data goes into this solution. It's done entirely using neural networks and residuals. There's not a single ounce of data. You can assimilate data into it, but in this case, no data whatsoever. You don't need it for this particular problem. Same thing with the burgers example, the first one we covered. In this case, because we're trying to infer parameters from data, needless to say, we need the data to do so. And then the last notebook I won't dig into for the sake of this conversation, but is the Helmholtz problem, and that just goes through and sort of shows how you would do a 2-dimensional problem, 2-dimensional steady state problem. You could take it and you could extrapolate it into being a 2-dimensional with time problem as well. But that's another notebook that on your own you can go and take a look at. It's on the same repository as the rest of them. So. Okay, so with that, it's very close to 3. I will take any further questions and any other comments or anything else.
So, Levi, do you want to talk a little bit about the development plan for the project and what you think about it and how you want to get our local developers and users engaged in the future development?
Yeah, absolutely. So
one thing you could do, Levi, is have a sort of Google groups for TensorDiffEq.
Yeah, okay.
And you know, I've seen that other projects have something like this.
TensorFlow does. Yeah, I'm subscribed to that. So as far as yeah, so that's a great thought. I've also thought about doing a specific developer. I think Marcelo emailed about a developer kind of get together where it's less about the execution and more about the development. Currently, I do have in the on the TensorDiffEq like main repository. I have a board here of kind of loose goals that I have that are kind of, some are a little fluffier than others. One is to implement a solid testing regime. That's something that I probably should have done, that I needed to do from the get-go, that needs to kind of go back and be recovered. Some doc strings to go in and add good documentation. Some stuff with the distributed training that needs to get fixed. You know, and then organizing the boundary condition generation. There needs to be some like optimizations built into the boundary conditions. So I have some outstanding things, and there's some thoughts organized here as far as like in the to-do board of this project. But of course, you know, as users are using it, so like Marcelo and Dr. Gilden can you know, find as they're using it, as well as, you know, we've been working with some folks from nuclear engineering as well, as they're kind of identifying issues and things that they want to implement, they're building those things out. I'm very open to pull requests. You know, I know Marcelo just the other day emailed me about a feature that he wanted, or actually a bug that was in there, and I, you know, verified. It was like, yep, okay, that works really well. Thank you for doing that. So more than happy to, you know, open an issue on here and say, hey, I'm going to work on, you know, fixing this thing or adding this feature. You can open a work in progress pull request as you're working on it, and we can kind of discuss it a little bit as well, meet by email, etc. And whatever features you're interested in adding, or whatever features are unique to your problem set. For instance, if you're in Aero, you may have a different feature that you need than somebody working in Mean, you know, these sorts of things. So kind of building the foundational building blocks, but as we identify specific features that need to be used, or that can be added for specific problems, you know, 100% open to that conversation. But as far as initial directions and you know, kind of stuff that I've been working that I know are weaknesses in the package, is kind of starts here, and they're really big things. They're sort of easy things to work at, like building out some tests, working in the doc strings, and building doc strings out for, you know, inputs and outputs. You know, just simple things like that I need to circle back to. Can also be sort of easy, you know, good first issue style things that people can hop on and contribute to if they want to.
Yeah, actually, one thing I think we can do right away is, you know, if anyone is interested in using TDQ for their project, we can host probably a page that lists, you know, highlights their work on our website, and it will be, you know, good starting point for others to refer to your work and get everyone connected.
And that's 100% true. So on the notebooks page here, I have kind of open, like kind of a call for you know, pull requests. If you're interested in adding a notebook because you you know, did some cool stuff and you want to open a PR to add to this, you can, you know, feel free to go in and you can fork this for yourself and add a PR or add a Python notebook to this page, and you know, we can kind of have a user base of I think the term floating around lately has been a model zoo of different implementations or different types of use cases that the package has helped with. So that's absolutely, so that was kind of the intent for this page, of this notebooks page, was one, for me to add examples of, you know, different types of implementations, but then also others, as they're building things out, can say, hey, this worked really well. This heat conduction problem worked really well, or I was able to change this to do this, and this is how I did it, and put the notebook up.
Okay, any other questions? If we have,
I actually do not have a question. Just would like to congratulate all the team and the developer, the Levi. It's a very interesting code and very well documented, and I am very interested in using and maybe contribute it if I can.
I appreciate it.
Thank you. Thank you.
Thank you. We put a lot of time into it, and unfortunately, I didn't get a chance to dig super deep into the documentation, but done the best I can to, you know, there's still some things that I know are missing from this that I want to add. But if anybody is interested in contributing or can find something, you know, something in the docs that makes things more clear, just because you mentioned the docs and I kind of blew straight through that earlier in the talk, you know, this is also a repository that's available to go in and open a PR on. And, you know, if you find something in there that you want to change, or that an example that worked really well and you want to add it to that, please feel free to do so. So
nice. Thank you.
Thank you for your kind words. Do appreciate that.
That's great. So I think that's all for today, and I'll send out a follow-up email, and I'll invite you all probably to a Google group or mailing list that Levi and I will try to set up, and we'll follow up with all of you guys if if there are any future collaboration or interesting project you want to work on, and we'll share the information through the mailing list.
Okay.
And thank you all so much.
Okay.
All right. Thanks,
Sure.
Dr.
Thank you, Levi. Thank you, John.
Great.
Bye.
Thanks, Levi. That was great.
Thanks.
Thanks,
I appreciate it.
thanks,
Yeah.
Ulysses. And-
Thank you, Eduardo.
Yes, thank you.
Bye.